Hello everyone, welcome to the Introduction to Electrical Engineering course. In this lecture, we will discuss about the characteristics of DC motor. Mainly here we will discuss the characteristics of the DC shunt motor. DC shunt motor. So when we say characteristics of DC motor, we need to study the characteristics of the torque versus armature current, speed versus armature current, and speed versus torque. So we need to study these three characteristics for the any given DC motor, either it may be a shunt motor, series motor, or compound motor. So in this lecture we will discuss about the characteristics of the DC shunt motor. So to discuss the characteristics, the basic things which we need to know is the torque equation and the EMF equation. We already know the EMF equation in the DC motor, that is back EMF is equal to, it is 5ZNP by 60, where phi is the flux per pole, Z is the number of conductors, N is the speed of the motor, P is number of poles, where A is the number of parallel paths. So for any, once you design the DC machine, the number of conductors remains constant, the number of poles remains constant, and number of parallel paths, either it may be for wave winding or lap winding, it remains constant, and number 60 is also constant. But the depending on the current and the load connected, this flux value and this speed varies. So these are the variable quantities, these are the variable quantities, these are the fixed quantities. So variable quantities, since when speed varies, flux varies, the back EMF also varies. So we can rewrite this equation as in terms of, so back EMF is directly proportional to flux and the speed, or we can rewrite this speed is directly proportional to back EMF and indirectly proportional to flux. So same thing is given here. N is directly proportional to back EMF and indirectly proportional to flux. So with these relations we can easily draw the characteristics of various characteristics of the DC shunt motor. One more is the torque equation. We know the torque equation, it is the torque developed in the armature is equal to 0.159 into the armature current into flux into Z into P divided by the number of parallel paths. So similarly in this, Z remains constant, number of conductors for any machine once you design, the number of conductors remains same, number of poles and number of parallel paths remains constant. Only variable is the armature current and the flux. So the torque is directly proportional to flux and the armature current, it is directly proportional. So with these two relations we can easily draw the characteristic curves for the DC shunt motor. So before that we need to understand, in case of series motor and as well as shunt motor, the nature of the flux. Let us understand for the shunt motor. To understand this shunt motor in a better way, let us draw the diagram, shunt motor diagram. This is the armature and field winding is connected in parallel with the armature. Here is the applied voltage, here we will have a back EMF. This is the current flowing through the field winding, it is ISH, and here current flowing through the armature, it is IA, and this is the load current IA. So whenever the current flowing through the field winding, this field winding changes, the flux produced by the field winding also changes. If there is a high current, the flux produced will be high. If there is a low current, the flux produced will be low. So in this case, for a DC shunt motor, the applied voltage, it is always constant. For a DC motor, the applied voltage remains constant, it will not change. And once we design the machine, the field winding resistance, RSH, field winding resistance, this also remains constant, and we know the relation V is equal to ISH into RSH, or we can write ISH is equal to V by RSH. So once you apply the voltage to DC motor, the applied voltage remains constant. So this is a constant, and resistance of the field winding also remains constant. So from this we can say that the shunt field current is also constant, since the ISH is directly proportional to the flux produced in the field winding. If ISH increases, flux produced increases. If ISH decreases, flux produced decreases. Since in shunt motor the ISH remains constant, the flux also remains constant in case of the DC shunt motor. Flux remains constant in case of DC shunt motor. So with this understanding, we will move on to the different characteristics of the DC shunt motor. Before that, let us understand the series motor also. Series motor, what will be the nature of flux in case of the series motor? So since it is a series motor, it will be like this. So here we will be having ISC, and this is the current ISC, the load current IL. So here the current ISC is equal to IL, and which is also equal to the current IA, So the flux produced in the series field winding depends on this load current. This load current, it is not constant, it is always varying depending on the mechanical load connected at the armature of the DC series motor. So this IL always keep on changing, so which means IA also changes, ISC also changes, and the flux produced is also changes. So from this we can say that ISC is directly proportional to phi, or IA is directly proportional to phi in case of the series motor. But in case of the shunt motor, the flux is independent, it is always constant. But in case of series motor, flux depends on the load current or series field current or armature current. So with this understanding, let us move on to the characteristics. The first characteristics is the torque versus the armature current IA. So this we can easily draw from the relation torque is directly proportional to flux into IA. We already know this relation from the torque equation, that is this equation. From this equation, torque is directly proportional to phi into IA. So in case of here we are discussing only about the shunt motor characteristics. First we are discussing about this shunt motor characteristics. Okay, that is first characteristics is torque versus armature current. So we know this relation for any motor, the torque is directly proportional to flux into armature current. For DC shunt motor, we know that the flux remains constant. So therefore we can write this as torque is directly proportional to IA. So if we plot the graph with respect to torque with respect to armature current, since both are directly proportional, the graph will be linear. When IA increases, the torque also increases. So this is the torque versus armature current characteristics of the DC shunt motor. Second characteristics is speed and armature current characteristics. Speed and armature current characteristics. Now we need to establish the relationship between the speed and the armature current. So to understand this, let us again write the relations. N is directly proportional to, we know it is EB by phi, EB by phi. Since this flux in DC shunt motor remains constant, so speed is directly proportional to back EMF here. Speed is directly proportional to back EMF. Now we need to write the relationship between the back EMF and the armature current. So if you know the relationship between the back EMF and the armature current, we can relate it to the speed. So for a DC shunt motor, EB, we know this EB equal to V minus IA RA. V minus IA RA. So from this equation, now let us understand how this IA is related to the EB. Since once you apply the voltage to the DC motor, the voltage remains constant. IA changes depend on the load, and RA also constant. So now if the IA increases, since this V remains same, V minus, if IA increases, the negative value increases. Negative value increases means the net EMF, back EMF will decreases. So if back EMF decreases, since back EMF is directly proportional to N also decreases, or vice versa. If IA decreases, here, the negative net value back EMF will be increases. Back EMF increases. If IA decreases, back EMF increases, thereby speed also increases. So we can say that speed and N both are indirectly proportional. Speed and N both are indirectly proportional. So if IA decreases, N increases, or if IA increases, N decreases. So if you plot the graph for this, we will get the plot for speed with respect to the armature current. So as IA increases, our speed should decrease. So your plot will be somewhat like this. It is decreasing. So this is the speed and armature current characteristics. Third characteristics is speed versus the torque. We know the characteristics of speed versus armature current. If armature current increases, speed decreases, and we know the relation between torque and the armature current. For a DC shunt motor, it is directly proportional to IA, since flux remains constant. So torque directly proportional to IA. As IA increases, torque also increases. So torque increases, IA increases. When IA increases, N also increases, right? When IA increases, so we know the relation between IA and N. It is indirectly. N and IA, it is indirectly. So as IA increases, torque increases. As torque increases, the speed will decrease. As IA increases, speed will decrease. Since IA is directly proportional to torque, when IA increases, torque also increases, but speed will decrease. So for this relation, N is indirectly proportional to T. Just we are replacing IA by T. So N is, as torque increases, your speed will decrease. So if you plot the graph characteristic for DC shunt motor with respect to speed with respect to the torque developed in the armature. So as torque increases, the speed should decrease. So this is similar to the second characteristic, that is speed versus armature current. So both characteristics, speed versus armature current and speed versus torque, remain same for the DC shunt motor. So this is the characteristics of the DC shunt motor. We will continue some more topics in the next lecture. Thank you.